It's time to make a start. So the organisers passed out a questionnaire. So if you could, before lunch, deposit these at the front of the room, that would be helpful. So we've got two more talks before lunch. So our first speaker is Benjamin Peherstorfer. He recently moved, I think it was recently, about a year ago, to the University of Wisconsin-Madison, where he's an assistant professor in the Department of Mechanical Engineering. He has lots of research interests, according to his webpage, including computational statistics, Bayesian inference, and in particular, multifidelity Monte Carlo methods. So you should know that we had a reading group here a few weeks ago. One of the working groups that were established in January to try and connect people in statistics and applied mathematics had the name of multi-level/multifidelity methods. So several people here have read one of your papers, and I'm sure they'll have lots of questions for you afterwards. So you're going to talk to us about multifidelity methods and adaptive low-fidelity models.
Okay, thank you very much for that nice introduction. Thanks to the organizers for setting up this nice workshop and giving me the opportunity to present some of our work here. So in the first part of this presentation, I wanted to talk about multifidelity methods with adaptive low-fidelity models, and then in the second part, depending on time, on multifidelity methods for rare event simulation. Now, I have many collaborators on this work, and I will point them out as I go through the slides. Okay, so our starting point is that we have an uncertainty quantification problem, and I won't be more specific at this and on the first few slides. An uncertainty quantification problem that we want to solve with a sampling-based approach. So this typically requires us to evaluate a model within a loop many times in a row for these different inputs, for different parameters, different coefficients. And the typical situation is that we have given a high-fidelity model. I call it a high-fidelity model, which entails a large-scale numerical simulation and gives us the quantity of interest that we want to have with the accuracy that's required by our problem at hand. So in the following, we will consider the high-fidelity model as our truth model. But this high-fidelity model is expensive to evaluate. Additionally, we often have given surrogate models which approximate the quantity of interest that gives the high-fidelity model, introduce some approximation error, but compute that approximation often orders of magnitudes faster than the high-fidelity model. And the purpose of this slide is to really point out that there's a full breadth of surrogate model types available that we typically can use. We have, for example, data fit models that ignore that often there's a PDE underlying our high-fidelity model and simply fit, or not simply, but fit a function to the input-output data given by this high-fidelity model. Gaussian process regression is one typical example. We can think of coarse grid approximations. I said already there's often a PDE underlying our high-fidelity model. We can discretize this PDE on different grids and get this classical multi-level or hierarchical structure on the grids, and so control error and costs. Gianluigi and Boris already talked about reduced models and model reduction, so we can use these projection-based reduced models also as a surrogate model. And even in some situations, we might have simplified models, so simplified physics models available, where we have some domain knowledge about the high-fidelity model and can drop some physics that might be not that relevant, come up with a surrogate model that introduces an approximation and gives us that approximation with much lower cost than the high-fidelity model. Now, the classical approach of using these surrogate models to speed up the sampling-based task that we are interested in here is to use a surrogate model instead of the high-fidelity model. So to replace the high-fidelity model with a surrogate model, and I like to think of the sampling-based techniques such as Monte Carlo and stochastic collocation as loops, where we receive an input, we need to evaluate the model, we compute the output, and then repeat this many times. Now in this classical approach, the high-fidelity model is replaced with the surrogate model. This gives often fantastic speedups, but it's also clear that the error of this surrogate model is introduced in the overall estimate. For example, in the error, for example, in your estimate of the expected value that you want to have, or in the samples of your posterior distribution in case you have a Bayesian inverse problem, and so on. So it is critical that there is a rigorous error control for the surrogate model available to use such an approach, and Gianluigi talked about this in his presentation, for example, where error estimators are critical. Now, we want to go a slightly different, with a slightly different approach, what we call a multi-fidelity approach, where we say we do not want to use only the surrogate model or only the high-fidelity model. Rather, in our loops, we want to combine both models. We want to have the surrogate model to obtain some speedups in certain situations where it is possible to use it without introducing an error, but we allow occasional recourse to the high-fidelity model to establish accuracy guarantees. Whatever that exactly means, we'll make this more precise when we go to the concrete methods. So the idea here really is, even though our surrogate models are wrong, they might still be useful. And often we don't only have one surrogate model here, but we have typically many surrogate models that we can use. And if you are interested in multi-fidelity methods beyond the things that I present here, we have a recent survey paper in Science Review that is co-authored with Karen Wilcox and Max Gunzberger that might be of interest. Okay, so this kind of sets the stage. We want to combine multiple models, and then we need to ask questions of how do we combine these models, how do we balance work among those models. And in this first part of the presentation, I would like to talk about this adaptive multi-fidelity Monte Carlo approach. And I already said the models that we use are wrong in a certain sense, but they still are useful. So the question is, how much should we even invest in constructing a surrogate model? So how much effort should we spend on constructing a surrogate model, improving its approximation quality with respect to a high-fidelity model, versus just spending all of the time using the high-fidelity model? And this is a question that I would like to answer with in this first part. Okay, so let's be a bit more concrete of what we are interested in here. I say we have given this high-fidelity model. I simply denote it as a function f that maps inputs onto outputs, and we have given a random variable in a suitable probability space, and then we're interested in the expected value of this high-fidelity model output under this random variable c. So this s is the quantity we want to estimate. Now, standard approach is to use, for example, standard Monte Carlo for this, and I have the estimator up here to fix the notation. We have realizations C1 to Cm of this random variable, evaluate f at those realizations, average over them, and get this standard Monte Carlo estimator that I denote here as f bar and m for the number of realizations or the number of samples. And now the key challenge is that this standard approach is too expensive for the models, for the high fidelity models we are interested in. So we say we want to leverage surrogate models for variance reduction and ultimately runtime speedup. Variance reduction in the sense that we want to come up with an estimator that has a lower variance than this standard Monte Carlo estimator with the same cost. And now there's tons of work on doing this. And of course, the first what I want to mention here is multi-level Monte Carlo. Many people here in this audience work on multi-level Monte Carlo. Many people in this audience have pioneered multi-level Monte Carlo in the PDE setting. There's also work on the reduced basis method and control variates, on data fit models and control variates, on control functionals, and I will come back to this a bit later. There's work on information reuse. So for example, in an optimization loop, one can reuse data from previous optimization iterations as control variates for subsequent iterations. And then there's work that we have done recently that's we termed it Multifidelity Monte Carlo, which really has the goal to combine these general types of surrogate models, heterogeneous types of surrogate models that I've shown on the first slide. And we will build a bit on this, but actually we will have only two surrogate models where this boils down to well-known standard control variates. Okay, so let's have a look at control variates and only two models, where we have, again, f as our high-fidelity model, and now we have one surrogate model, f1. And we still want to estimate this expected value of this high-fidelity model output random variable. We can set up here a control variate estimator, I denote it as s hat, where I have here the standard Monte Carlo estimator that takes m naught realizations of the input random variable and evaluates the high-fidelity model and sets up an estimator. And then we have here a control term, and this control term comes from the surrogate model. It evaluates the surrogate model at m1 and m naught respectively realizations of this random variable c. So m naught is the number of times we evaluate the high fidelity model, m1 is the number of times we evaluate the surrogate model, and gamma is the control variate coefficient. And what control variates essentially do, they exploit the correlation, and here I denote the correlation coefficient with rho 1 between the output random variable corresponding to the high fidelity model and the output random variable corresponding to this surrogate model. Okay, so what about costs and error? These are the two things that we are interested in. Costs of this estimator, here what's typically considered is the cost of evaluating the models. So in that case here we have C of S hat is the number of times we need to evaluate the high fidelity model times the cost of one high fidelity model evaluation, which is this W naught, plus the number of times we evaluate the surrogate model times the cost of one surrogate model evaluation. Okay, so this is the cost, and then we are interested in the mean squared error, and for the optimal M naught star, M1 star, gamma star, optimal in the sense that we prescribe a certain cost that we allow. So we say the cost of this estimator can be the budget P, and then we want to minimize the mean squared error. If we select those components, then we obtain this mean squared error for this control variate estimator. This is all well known. The critical thing is that this depends on the budget P that we are ready to invest, and it depends on the correlation coefficient between the output random variables, and it depends on this cost ratio. Now, the critical thing for us is that this gives us more or less, or that these here is more or less an optimal balance between how often we need to evaluate the surrogate model and the high fidelity model to minimize the error. But it does not take into account the cost that we need to invest in constructing this surrogate model. Where is it? Here. In constructing this surrogate model. If you think back of the surrogate models that I mentioned in the beginning, projection-based model reduction or data fit surrogate models, we typically have to evaluate the high fidelity model multiple times to come up with these surrogate models. And what we are interested in now is how can we trade off the cost of constructing the surrogate model with the cost of then sampling and evaluating the models. Okay, so let me emphasize this point. This is how I see the traditional approach of using surrogate models in Monte Carlo settings. First, models are constructed with a certain goal in mind, for example, to satisfy a certain bias constraint, and then the constructed models are used and optimally combined in the sense that the samples are selected such that the overall error is minimized. What we are now interested in is that we say in our multi-fidelity setting, we have the high fidelity model together with the surrogate model, and we would now like to find out how accurate our surrogate model should be, so how often should we adapt it, or in what sense should we construct it, such that we minimize the error of the corresponding estimator. And the idea is that we want to trade off the deterministic approximation with the sampling. Okay. So let's have a look at this in more detail. So again, we have the high fidelity model. I denote or I say the cost of evaluating the high fidelity model is 1. I just normalized it, makes the formulas a bit easier. And then we have now this surrogate model Fn, where n is now a parameter. And that parameter n controls the properties of the surrogate model. First, we say that the correlation coefficient rho n converges to 1 with a rate alpha. So the correlation coefficient between the high fidelity model output random variable and the surrogate model output random variable. And second, we say that the costs may increase with a rate beta. So this is similar things as they are, for example, used in multi-level Monte Carlo. Now what the additional part for us is that we say for constructing the surrogate model Fn, we also need to invest n evaluations of the high fidelity model. And since our W naught is 1, we have to invest costs n. Okay, and again, let me emphasize that in the model reduction setting, it is critical to take these costs into account because often we really have to evaluate the high fidelity model multiple times. Okay. Now, what this adaptive multi-fidelity Monte Carlo approach now wants to do, it wants to split the total budget P that we have available. It wants to split it between constructing the surrogate model, so how many high-fidelity model evaluations should we invest in constructing the surrogate model, versus the rest of the budget that we then should invest into sampling the high and the low-fidelity model. So if we spend n evaluations on constructing the surrogate model, we get a certain surrogate model with a certain correlation coefficient and costs, and then we have the budget p minus n left for sampling. So when we look then at the corresponding mean squared error of our AMFMC estimator S hat n, where again n is here this parameter that controls the surrogate model, then we have a very similar term as on the previous slides, except that now the budget is here not p, but it is p minus n, because we spent the first n evaluations on constructing the surrogate model. And now we want to do what people typically do in this setting. We want to find an n such that we minimize the error of this estimator. So we want to minimize the error, and we have a constraint on n that n has to be greater than 1, and it has to be less than p to be a reasonable choice for the number of times we evaluate the high fidelity model for construction. Okay, we will not directly work with this mean squared error here, but rather consider an upper bound. One can upper bound this error up to a normalizing constant with this term here, where you can again see here the budget that's left for the sampling, and the rate corresponding to the error, and the rate corresponding to the costs. And this is now what we want to minimize. Okay, so let's have a look at the corresponding objective function g of n, which is exactly the bound that I have shown in the previous slide. Now, what we could show is that this one is convex in the interval that we are interested in, so between 0 and p. So there exists a unique n hat star that minimizes this g. So there exists kind of a sweet spot how often we should evaluate the high fidelity model for constructing the surrogate model. Now, what else can we say about this n hat star? So of this quasi-optimal number of adaptation, quasi-optimal because we minimize a bound, an upper bound, not directly the error. We can upper bound n hat star for small budget. This will become clear later on what that exactly means. For small budget, we have that n hat star is less or equal than alpha over alpha plus 1p. Well, this is true always, but for small budgets, this is a good bound, and I will say this later on. And then we can also say that the number of adaptations is bounded for increasing p. And I think this is an interesting result, because it tells us that there exists an n bar star that is independent of the budget that we have available, that upper bounds our n hat star, so that upper bounds the number of evaluations we should spend on the high fidelity model. And this more or less means that even if you have an unlimited budget, at some point you should stop improving your surrogate model and should not improve it forever, but at some point it's better to stop. And I think this is an interesting result, and we'll see this later on in the numerical results as well. Okay, so this is what we can say on this n hat star. Let's now define this AMFMC estimator S hat star n, which uses this n hat star, this optimal value of this upper bound, for constructing the surrogate model f n hat star, and then uses the rest of the budget for sampling in this classical control variate sense that I have shown on one of the very first slides. Okay, now what else can we say about this estimator now? And the first one to consider here, this case where the cost of evaluating the surrogate model is 0. Now, this is unrealistic, and we will not have this in practice, but it gives us some insights on what's going on. And what we can show in this setting here is that this mean squared error decays or has a cost complexity of p minus 1 minus alpha. So we find this alpha rate, this rate with which the surrogate model converges with respect to this correlation coefficient, we find that rate here. And again, I want to emphasize that this is true only if the cost of evaluating the surrogate model is 0. And we can interpret this in the sense that if this holds, then we more or less know the expected value of the surrogate model, and then this approach boils down to something similar as what has been considered by Mark Girolami and collaborators in his work on control functionals, where they also show rates similar to this. Okay, but again, for us this is not realistic, but it often helps us to understand the case where the cost of evaluating the surrogate model is very low, And in the surrogate models that we're interested in, we often have, 6, 7, 8 orders of magnitude speedups compared to the high-fidelity model. Okay, now what else can we say about n hat star? I don't have an analytic solution to it, but we have shown that this optimization problem is one-dimensional and it is convex. So it is relatively easy to find the numerical solution to this n hat star, but we do not have the analytic solution to this. And this is also what we will use in the following. We use numerical solver, we use here fmin_con to solve the corresponding optimization problem. Again, it's 1D and it's convex. Okay, and this brings me to the numerical result. So we have defined this AMFMC estimator that adapts the surrogate model up to a certain point that's quasi-optimal. And now we want to apply it to some model problems and see how it performs there. The first problem that I want to consider is from this model reduction benchmark suite that you can find on this website, and you can also download all the code there. This is an anemometer where we have a channel, and in this channel there is a fluid that flows through the channel, and there are two sensors, a sensor left and a sensor right, and the heater is in between. And what this device should do is it should sense the velocity of this fluid. So it heats the fluid here, it senses the temperature left and senses the temperature right, and then from this are the temperature contours. From the difference from the left sensor and the right sensor, it can infer the velocity of this flow. The high fidelity model is a convection diffusion equation, and again you can find all the details here and on this website and the corresponding papers that are cited there. It's discretized with finite elements, and the high fidelity model has about 30,000 degrees of freedom. Now it's a time dependent problem, and we time step this until a certain time and then estimate the corresponding expected velocity. The inputs are uniformly distributed in this three-dimensional input domain. Okay, what about the surrogate model? As surrogate model, we use here Gaussian process regression, and we train this Gaussian process regression on n evaluations of the high fidelity model. So we take n realizations of this input random variable, evaluate the high fidelity model at those n realizations, and then train the Gaussian process model on those outputs. And this n is what we want, what AMFMC tells us to do, what AMFMC optimizes for. Now to apply to AMFMC, we need the rates and we need the constants. For Gaussian process regression, they are available in certain situations. We simply use here a numerical approximation of these rates. We take a couple of samples and estimate the error. The error is here this 1 minus rho n square, and then take a regressor through the data and come up with a certain rate. So this is a very hands-on approach on this numerical result. This gives us the alpha rate, and we can also do the same for the cost rate. Okay, and these are the runtime results. We have here the budget P, or the runtime that we are ready to invest, versus the mean squared error. We see here classical standard Monte Carlo that uses the high fidelity model alone, and we see here this AMFMC approach. Now, speedups are obtained here in the end of about 2 orders of magnitudes compared to using only the high fidelity model. And we also see something that I discussed a bit in the theory part, where I said the classical Monte Carlo rate for the mean squared error is p minus 1. For this AMFMC, because the surrogate model is so cheap in the beginning, we achieve p to the minus 1 minus alpha. But again, I want to emphasize this is only in the beginning, and we will later see that, of course, in the end it will level off and become the standard Monte Carlo rate of p minus 1. But in the beginning, this is kind of how we explain this behavior. Now, how does the n look like? How does the n that we optimize for look like? This is the budget p versus the n, and you can see here in purple the n, and it happens what we predicted with the theory. In the beginning, there's an increase, and at a certain point, it levels off and does not increase anymore with p. You can also see here this upper bound that I have plotted, and now it becomes clear what I mean with a small budget. For a small budget, this upper bound seems reasonable, but at a certain point when this n starts to level off, then this bound does not make sense anymore because it keeps increasing, and we get it's not a good bound anymore. But this is really the point where things become interesting, where this n levels off at some point. Okay, so how does this adaptive approach now compare to an approach where the models are fixed, where they are static? And this is shown here. This is again the budget versus the mean squared error. This is orange. The orange curve corresponds to static control variables where we have a Gaussian process model with n is 57, from n is 57 high fidelity model evaluations. And the yellow curve corresponds to static control variables where we have n is about 600 evaluations of the high fidelity model. You can see in purple the AMFMC approach, which touches these curves in the beginning, but then while these are suboptimal after a while because the model is not further adapted, the AMFMC keeps adapting to the right n, and so can improve upon these static approaches. Okay, now all what I have shown was in kind of this pre-asymptotic regime where we have this faster decay of the error than in the asymptotic regime. I want to show you a second example where we actually see these two different behaviors. Here this is a beam problem where the beam is attached to the wall on the left, and then there's a force applied to the beam, and we're interested in the displacement, in the expected displacement after a few time steps. And the inputs are here the length and the height, which are uniformly distributed, and as I said, the output is the quantity we want to estimate is the expected displacement. Now the high fidelity model for this problem is available in the literature, and I'm happy to share the reference with this. And we use again a Gaussian process model as our surrogate model and estimate the rates alpha and the rate beta in a hands-on approach here numerically. And these are the results that we obtain in terms of runtime. Again, the budget p versus the estimated mean squared error over a couple of runs. We see here the standard Monte Carlo with the rate p minus 1, and we see here this AMFMC approach. And you see exactly in the beginning we have this faster error decay, but at a certain point, as we predict, it levels off and it gives us the standard Monte Carlo rate. But still, they are shifted. And this AMFMC is especially interesting, of course, in this region here, because in this region we have to choose n carefully such that we obtain a low error. When we are somewhere out here, then n is constant, and there's no change necessary anymore. Okay, but often we are really interested in this pre-asymptotic behavior. Okay, so this was the first part on this adaptive low fidelity model. So how much should we invest in constructing the surrogate model? In the second part, I wanted to say a few words on rare event simulation with multi-fidelity methods, and this is collaborative work with Karen Wilcox and Boris Kramer, who is here today as well. Okay, so a quite different problem that we're interested in here. We say again we have a high fidelity model, and there's a slight change of notation now that I say F1 is the high fidelity model with a certain cost W1, and then we have given here a threshold T, and we are on a random variable, and we're interested in estimating the probability that the output of this high fidelity model is less than T. And we are interested here in the case where this PF is small, where we have a kind of a rare event. And the problem that everyone in this room knows about is that standard Monte Carlo, the coefficient of variation of the standard Monte Carlo estimator grows with 1 over PF, so becomes worse as the probability as this probability decreases. We can also pose this as an estimation problem of an expected value when we define an indicator function that depends on this threshold T, and this 1 means that the high fidelity model is evaluated. It gives 1 if this condition is satisfied, and it gives 0 otherwise. Okay, so there's again a lot of work on this in the community on using surrogate models for speeding up rare event simulation. I distinguished here between 3 categories. First one are these 2 fidelity approaches that have a low fidelity model, a surrogate model, and a high fidelity model. And I want to point out 2 works especially. The first one is by Dong Bin on switching between models, and the second one is by Bang Chen on reduced basis method and using error estimators to switch between models. Now there's work on the multi-level methods for rare event simulation, building on multi-level Monte Carlo, for example, or Elizabeth Ullman's work on the subset method with a multi-level hierarchy. And then we also have some work on combining multiple general types of surrogate models where we want to insure against certain surrogate models that are not accurate, for example. Okay, we want to use here importance sampling. Just on one slide to clarify the notation, we want to find a biasing density Q with a larger support than the nominal density, and then reformulate our estimation problem with respect to this biasing density. And then the goal is that we find a biasing density such that the variance of this reformulated problem is much smaller than the variance of the original problem. And we want to use surrogate models for this, of course. Now, what we call the direct sampling approach is to simply take a surrogate model. When you look at this biasing or on this nominal density here, and here's this threshold which defines in which tail behavior we're interested in. What we call the direct sampling approach is to use a surrogate model to sample this extensively and then find a few samples in that region here, and you learn something about the region, you can fit the density to that region or come up with some other way to find a biasing density for this corresponding threshold. Now what we are interested in here is sometimes called very rare events, where this threshold is, say, out here, and then we would need to sample this billions and billions of times, and the sheer number of samples is what's really the challenge here. So we cannot even afford to evaluate the surrogate model at so many samples. And what we build on is the cross-entropy method, where which realizes that this threshold T controls the rareness of the event. And it says, let's start with this nominal density, but instead of directly going for the T, this cross-entropy approach suggests to start with a T1 that's larger than the original T1 is interested in, and then iteratively builds biasing densities until it hits the T that it is interested in. And in each step, the density of the previous iteration is used as a biasing density for the estimation of the next biasing density. Okay, so this is what we build on, and I have it a bit more in detail here. Let's say we have steps I is 1 to T. Then we know that for each Ti, there is a corresponding optimal biasing density, optimal in the sense that the variance is then set to 0. This optimal biasing density is known up to a normalizing constant, which is exactly the quantity we want to estimate, so we cannot directly use it. But the cross-entropy method now says, let's consider a family of parameterized distributions, and let's find a QVI, so with a parameter Vi, such that the KL divergence between this optimal density and our density of this family is minimized. And this optimization problem can be reformulated into a maximization problem of an expected value, which in turn can be replaced by a Monte Carlo estimator here. Okay, so this is an optimization problem that has been solved, that has to have been solved in each step. The problem is that still we have these TIs in there, which still lead to a rare event in a certain sense. So we have not gained anything, or the cross-entropy method has not gained anything at this point. So what the cross-entropy method then does, and I already said this in the beginning, it uses the densities of the previous iteration as biasing densities for the subsequent steps. So let's say QVI minus 1 is the density of the previous step, and then it takes this QVI minus 1 as a biasing density for finding the density at step I. Here you can see this expected value with respect to Vi minus 1, and then a reweighting term to correct for the bias. And this is done for all the steps. And once this biasing density has been found, then classical importance sampling is used, where now the corresponding CE density QV star is used as the biasing density, but the indicator function corresponding to the high-fidelity model is used and evaluated to obtain an unbiased estimator. Okay, now what we want to bring in here are now surrogate models to speed up the computations of this biasing density, and for that we first need to understand where the costs are of this CE method. This Ti is the threshold that we define in each step, and this Ti we define using a quantile parameter rho, and I give you a typical interval that we choose, but of course this is a parameter of the method. I'm giving you this typical interval to point out that it's not a very critical parameter. Now this Ti is the rho quantile of the corresponding biasing distribution of the previous step. And then we can say that the number of steps that we need to find these biasing densities, we introduce a minimal step size, or not we, but that this has been done, introduces a minimal step size, and then this t can be bounded as t minus 1, as t1 minus t over delta t. So t is the total number of steps that the C iteration has to take, and this is a very naive and simple bound for this. The thing is that we want to point out is that then the costs of this estimator depend on the difference of this t1, the one that we start with, and the t that we are actually interested in. And what we now propose is to use surrogate models to reduce the t that we have to start with when we use the high fidelity model. So let's again say we have here the surrogate models. We have on the left, let's consider we have these surrogate models, and let's now consider a case where we have the surrogate model and the high fidelity model, so only two models. On the left you can see the surrogate model, and with that we start and iterate until we hit our t value, standard cross entropy method. But then when we are interested in the high fidelity model, instead of starting with the nominal density again, we say we start with this density coming from the surrogate model and iterate, and then probably need to iterate only a few times to correct, corresponding to the error that's introduced by the surrogate model. But the important step is that we correct here with the high fidelity model. Okay. Now, in interest of time, I skip here parts of the analysis which is not satisfactory, at least to me, because it only tells us that we are not doing anything wrong. We cannot show at this point that we are really better with this approach. And there are several things that we are still working on and trying to find out how, if there's something if there's something stronger that we can prove. So let me, rather the last few minutes, show a numerical result. And this is again the Poisson equation, or Laplace equation, where we have here a stochastic coefficient. We have two normally distributed random variables. We discretize this in with different mesh widths using finite differences, and then obtain the corresponding models. F1 corresponds to the model with the smallest mesh width, and F5 to the one with the coarsest one. And then we're interested in estimating the probability that this output is less than 1.4, and we did a reference estimate which said that we have in the range of 10 to the minus 9. So the probability of this is about 10 to the minus 9. We used high fidelity model evaluations to come up with this. So how does the multi-fidelity approach compare to the CE approach that uses a single model only? On the left you can see the runtime that we need for constructing the biasing density, and this is where we can obtain speedups. This is where we use the surrogate models versus the coefficient of variation. And here you can see the CE that uses the high fidelity model alone, and here you can see the multi-fidelity approach that combines these multiple surrogate models that I have shown on the previous slide. Now what we're actually interested in is the total runtime that includes the final estimation step, where we always evaluate the high fidelity model. And what you can see here is that really the runtime, even the total runtime, is dominated by the construction of the biasing density. So significant speedup also with respect to the total runtime. Okay, final example that I want to show is this reacting flow example, where we have three models. We have a data fit model, which is simple linear interpolant from inputs to outputs. We have a projection-based reduced model constructed with proper orthogonal decomposition and discrete empirical interpolation method, and we have the high fidelity model that's derived with finite differences. And we have two uncertain inputs here with normal distributions, and then we are interested in the probability that the temperature in this reaction is below a certain threshold. And the probability when we take a reference estimate is in the range of 10 to the minus 6. Now when we apply our multi-fidelity approach, we obtain these results for the runtime of the biasing construction. Again, you can see significant speedups here compared to using only one model. When we consider the total runtime though, then you can see that here the total runtime is really dominated by this final step that requires evaluating the high fidelity model, and the speedups that we obtain here in constructing the biasing density actually boil down by quite a bit in the speedup that we obtain in the total runtime. Now, if we slightly extend this reacting flow example to 5 inputs with different distributions, then you can see that, again, runtime improvements are obtained for the biasing density, and that also the total runtime has a higher cost for constructing this biasing density, which we can see here by obtaining a significant speedup compared to using the high-fidelity model alone. Okay, and with that, I conclude by just saying this multi-fidelity methods, we realize that all models are wrong, but some are useful, that famous quote, and we want to leverage these surrogate models for speedup in situations where it is possible without introducing an error, and allow the recourse to the high-fidelity model to establish accuracy guarantees, which can mean different things. It can mean unbiasedness, or mostly meant unbiasedness in what I presented here, but there are other notions that we might want to establish with occasional recourse to the high-fidelity model. Okay, with that, let me thank you for your attention.
Okay, thank you for sticking so precisely to time. Anyone got any questions or comments that they'd? I think Henry, you're the first.
Yes, not in this field, but in sort of parallel fields where they look at means and variances, like robust engineering design. I always think it's a little bit dangerous just to put everything into a mean squared error. It would be nice to see the contribution from the mean, the bias, if you like, the bias squared, and the variance, because you might trade those two off against each other.
Yeah, this is thanks that you bring this up, because in our situation we have no bias. We say the high fidelity model is our ground truth, so there is no bias. We only have the variance. So maybe the comment should then be interpreted in the sense that I should not call it the mean squared error, but rather the variance. Yeah, because this S is this, and we have occasional evaluations of the high fidelity model which reduces the bias to 0.
On the other hand, just to follow it, on the other hand, you might do the trade-off, some of the bias, to decrease the mean squared error.
Yes.
So that's another strategy. I mean, some areas they fix the bias at 0 and then minimize the variance, but that's not necessarily optimal with respect to mean squared error.
Yes, thanks again for that comment. This is something that we're currently looking at if we still should trade off, and there are several estimators that are doing this. Yeah, you're absolutely right. It's a very good comment, thanks.
Any other questions? Yeah, Alex.
In the method that you showed where you first use the surrogate model and then go back to the high fidelity model and start from there, when you're trying to cut to sample from the rare event, when do you decide that you go back? And because the error might have grown quite a lot, and maybe you need to do that several times, go back to your high fidelity model.
You mean here?
Yes, exactly.
So we
Because then you start there, but maybe the error has, you need to control it somehow, because it might be massive, and then you go back, and you might have missed subsets of the input space where you should have sampled.
Okay, so the reason we go back to the high fidelity model is because the surrogate model is only an approximation.
Yeah,
so it does not.
yes.
Right. So we go back to the high fidelity model. Once we are with the high fidelity model, we don't go back to the surrogate model.
No, but okay, but then when do you go back? When do you decide that you go back and use the high fidelity model?
Oh, we decide when we hit this T. We adaptively select this intermediate T's, and at some point we hit the T, and then we go back to the high fidelity model.
Okay, but by that time, because you used an approximation,
Yeah.
the error might have grown enormously.
Yes.
So when you go back, you might be sampling from the incorrect
Right.
subsets in the input space. So do you have any idea of how to control that?
No, you're absolutely right, and the way we control this is by going back and then correcting with the high fidelity model. You're absolutely right. In the worst case, if you have here a surrogate model that's not accurate, then you might end up with something here where you need even more iterations than with the high fidelity model alone. That might happen. But what we say is that by going back to the high fidelity model, in the end, you will still come up with a biasing density that makes sense from a high fidelity model point of view. So this is kind of our correction step. But I understand your point. So I'm not sure, did I answer your question?
Yeah, we can discuss
Yeah.
further. Thank
Yeah.
you.
Okay, I suggest we stop there, and any other questions and comments should be deferred till lunch break, and thank our speaker again.